From NTHU, let's welcome.
Okay, so thank you very much for giving me this opportunity. I'm very happy to be here today. So I'm Tetsuya Hashimoto from National Johnson University. So today I'm going to talk about repeating rate of pulsar radio bursts with the pulsar radio telescope in China. Actually, this project is led by Yuri Uno in National Johnson University. And then my talk is based on this paper, which will be submitted very soon. And then also this work was conducted in collaboration with these people listed here. Okay, so let me get started. So this is the outline of my talk today. So let me start with an introduction about pulsar radio burst. And also let me emphasize the importance of classification of pulsar radio burst. And then I introduce the problem and our approach to resolve this problem. And then let me summarize our result and conclusion at the end of my talk. Okay, so first radio burst, so FRBs are mysterious radio signal which are really coming from extra galaxies. So I took a picture from our press release in this year, which was led by Ikebe-san in University of Tokyo. So this is kind of memorial detection in Japan. So this is only special for Japanese people, but this is a schematic diagram of detecting pulsar radio burst, which is really coming from this distant galaxy. So we say this host galaxy. And then there is a source which is emitting this radio pulse. This pulse comes all the way to the telescope. Then we detect this as a FRB. And then this pulsar radio burst, their duration is really short, which is millisecond time scale, but the brightness very bright, Jansky level. So far, more than 500 FRBs are detected using CHIME. However, we don't know that their origins. So this is a problem. Actually, throughout this meeting, we have several talks about the pulsar radio burst, including Shushen, next speaker, and then John, next speaker, and also 3 posters. Therefore, if you are interested in FRB talks, presentations, please come to these talks and posters. And then, what's the problem? Okay, so there are observationally 2 different types of FRBs. One is non-repeating FRBs, or recently people say one-off FRBs. So if you detect only one time FRB from the same astrophysical source, so we say non-repeating FRB, only one time. If you detect multiple FRBs from the same astrophysical source, then this is repeating FRBs. Now we know that more than 1,000 FRBs are happening on sky every day. So this is a lot. However, we don't know the origin of FRBs, so this is the problem in astronomy and astrophysics now. So, this classification between non-repeating FRBs and repeating FRBs is really fundamental to address the mysterious origin of FRBs. However, this is just a classification, it's still hard. Why it is hard? I showed a schematic diagram here. Let's say there is a true repeating FRB here. This is a right curve of repeater. There are 3 bursts here. However, unfortunately, our observation is always limited. The time window that we can observe is always limited. So therefore, in this case, for example, we can only observe this narrow time window to detect only one burst. In this case, it's obvious, right? We misclassify this object as non-repeating FRBs. So due to this problem, we even don't know whether the origin of repeating FRBs is the same as origin of non-repeating FRBs. So, to address this issue, actually problem is we really need long monitoring observations with high sensitivity to address this issue. So this is too expensive to conduct. So therefore, we need a really new method for this classification problem. To overcome this problem, we propose our solution, which is machine learning. So let's ask machine if it is repeating or not repeating. Actually, this work was done by this Oliver, who was NTHU student before. Now he moved to Korea as a PhD student. So he used this unsupervised machine learning algorithm to use this decent time economy catalog. And then interestingly, so he found that actually this confirmed repeating economies are located at the same position. They make really cluster in this projected 2D space, which are shown by red dots here. And also non-repeating economies are located at different positions in this projection, which are shown by black here. More interestingly, he also found that there are non-repeating economies which are really located close to the confirmed repeating economy sources, which are actually shown by blue dots in this diagram. So they are originally non-repeating economies in Chime catalog, but they are really located at the same cluster as repeating economies. So therefore, we say they are repeating economy candidates selected by machine learning. So actually, very recently, one of them, repeater candidates selected by machine learning, was confirmed to be an actual repeater by Chime. Because Chime Tech is a Canadian radio telescope which can detect many economies. Chime is scanning the sky every day, so therefore they always have a chance to identify new repeating economy sources. Then one of them was confirmed very recently. And then in this one, we use the first radio telescope in China, which is the largest single-dish radio telescope in the world currently. Fortunately, we were awarded 2 science programs regarding this repeating and non-repeating classification. And then in this talk, in 2021 and 2022. And in this talk, I include the result from 2021. Okay? But why fast? Why we want to use fast? So let me emphasize, clarify this point. So this figure, this is also again a schematic diagram. A cumulative number of economies in y-axis as a function of observed fluence is a kind of brightness of economies. And then from Chime's observations, it is already known that the slope of data distribution is minus 1.5 in this figure in log space. That means if we use the telescope that is 2 order of magnitude better sensitivity, actually this fast that we are using here is 2 order of magnitude more sensitive compared with Chime. If you use very high sensitive telescopes, actually you have 1,000 times higher chance to detect economies. So therefore, this is really clearly indicates the power of fast to detect repeating economies. But Chime is actually every day conducting FRB observations, so therefore actually they can accumulate exposure time on each source on sky. For example, typically Chime can achieve 10 to the 100 hours per source per year. This is the exposure time per source per year. If you use fast, actually you get this 1,000 or better chance to detect economies. So therefore, even if you only spend 10 minutes exposure on each source, which corresponds to about 170 hours of Chime in terms of chance of detection of economy repeater. So therefore, we use this fast radio telescope to observe 36 repeater candidates. The exposure time is really 10 minutes each. But still, you may wonder if 10 minutes is too short, maybe. But let me try to convince you. So, we actually, before observations, we actually conducted a very simple Monte Carlo simulation, assuming the famous active repeaters. And then, if all of our samples are active repeaters, actually we expect the highest expected number of repeater confirmation when we use the 10 minutes exposure on source, because we have a limited time of telescope. So, then in this case, if all of them are really active repeaters, we expect about 10 repeaters, if they are all active. Okay, then let's move on our results. So we carefully check the first data, and then down to SNR or 5 level. So if you are carefully look at this one, you may be able to slight feature here, vertical line, this one, you see here. But unfortunately, they are SNR 4 to 5 level. As a conclusion, unfortunately, we didn't detect anything with SNR higher than 7. But still, this can strongly constrain the repeating rate of our sample. Compared to previous ones, actually, we included 5 times more sample in this work to achieve 10 times better constraints than ever. So our constraint on repeating rate for each sources are shown by blue here, and the previous ones are shown by red. So we have about 1 order of magnitude better constraint on repeating rate of each source. And also, let me remind you that our expected number of FRB confirmation from this project is about 10 if all of our objects are actively repeating. In other words, so we didn't detect any, we don't have any confirmation. So that means in our sample, the number fraction of active repeaters should be less than 10%. So let me conclude my talk. So we try to combine machine learning and fast radio telescope, and then we selected repeater candidates by using machine learning methods, and then we conducted the first follow-up observations. Unfortunately, we didn't detect anything from this first year, but we achieved 5 times larger samples plus 10 times stronger constraint on upper limits on the repeating rates for each sources. From these observations, the active repeaters should be less than 10% in our samples. And then we are still conducting this follow-up observations using FAST this year, so therefore I hope I can present something more interesting result in next year. So I stop here, so thank you very much.
So we have. Now, please wait.
Okay. So how do you give like confidence levels when you say that machine learning separates into like different categories?
Actually, we didn't calculate the confidence level, but rather than that, we use a clustering algorithm to identify clusters. And then if you say in this way, so you can identify cluster groups, then if non-repeater belongs to that cluster which has repeating values, then we say this is candidate.
Just one question is that how is this like an autoencoder things, and you got it in space and you plot this in linear space and do the classifications?
Sorry, I didn't get your question. Sorry, could you repeat?
So is this machine learning like taking the light curves and I have an autoencoder and I have a linear space, then I have this distributions so that I have like different clusters? Is it do it by this way or other?
Say maybe quite simplified. So this is kind of nonlinear combination of observed parameters. So when you observe FRB, so you measure many different observables, say fluence, duration, spectrum shape, and scattering time, dispersion rate, many things, right? So this makes a multi-dimensional space of data distribution. And then this makes a nonlinear combination of this. And then try to optimize viewing angle to emphasize the different clusters of data distribution. And then, if I can add more, we try to identify physical meanings of this axis. This axis is in principle combination between different observables. Therefore, it's in principle hard to tell. But Oliver actually tried to identify because he did a significance ranking of each observed parameters, which most significantly affect the data distribution in this projection map. And then that was a spectrum shape actually. But the most important parameter is the highest frequency that you detect and also peak frequency of FRB. So both of these top two are related to spectrum shape. So that basically this different distributions correspond to different shape of spectra. That's a physical interpretation.
Thank you very much.
Thank you very much.
Thank you for the nice talk.
I'm not familiar with this research, but I just want to answer simple questions. Do you have a threshold about the repeating periods to classify repeating or non-repeating? Because non-repeater maybe just because the repeating period is 10 years or 100 years, so you think it's non-repeating.
Okay.
A single criteria on the time to classify that.
I see. I think that's a high in debate. Actually, among the identified repeating herbicides, actually, as far as I know, there are only 2 cases where we have periodicity. And then one is 156 or so, 156 days periodicity. And then another is 16-day periodicity. So this is a periodicity. But for others, actually, we don't know the time scale. So we are really trying to figure out.
Thank you. Okay,
we have to stop here. So let's